Hi all, we'll continue with module 3 time response of feedback control systems. Today the topic is first order and second order system. Before entering to first order and second order, we should know what is order of a system. Order of the system is given by the order of the differential equation governing the system. So I'll tell you once again, the order of the system is given by the order of the differential equation governing the system. It is also given by the maximum power of s in the denominator polynomial of transfer function. So you know what is a system, you know what is a transfer function. Now we are studying with respect to order. I'll tell you once again what is the order. The order of the system is given by the order of the differential equation governing the system. It is also given by the maximum power of s in the denominator polynomial of transfer function. The maximum power of s also gives the number of poles of the system, and so the order of the system is also given by the poles of the transfer function. So I hope you understood what is order of the system. Now we'll continue with the first order system. So you can consider the system over here. As you can see there, input is R of s and output is C of s, and the system which you have considered is 1 by st. And you can see a feedback over here. That feedback we can call it as negative feedback, and there is no value over there, so hence we will take it as unity. So if you have to find the transfer function of the given system. So you know that transfer function is nothing but output by input. So your output here is C of s and your input is R of s. So that you can write the transfer function as C of s by R of s is equal to G of s divided by 1 plus G of s. Actually, the equation is C of s by R of s is equal to G of s divided by 1 plus G of s into H of s. Here H of s is nothing but feedback. It is unity over here. So the equation has come like this. Now you have to substitute G of s is equal to 1 by st, because previously you have seen the diagram. The system which you have taken is 1 by st. So you take G of s is equal to 1 by st. Therefore, the given equation or transfer function we can write it as C of s by R of s is equal to 1 by st divided by 1 plus 1 by st. When you modify this, the equation will become 1 by st plus 1. The power of s is 1 in the denominator. As we are discussing that what is order of the system, we know that order of the system is nothing but we have to identify what is the order of the differential equation governing the system, or else the maximum power of s in the denominator polynomial of the transfer function. So we have seen the polynomial here. It is 1 by st plus 1. So in this s polynomial is having 1 as the order. So the given system is first order system. So we can rewrite, we can also rewrite the same transfer function as C of s is equal to 1 by st plus 1 into R of s. What is C of s? C of s is your output signal, and s is nothing but we are writing the equation in terms of Laplace. Otherwise, it will be represented as C of t. Similarly, R of s is the input signal. If it is not in Laplace, it will be R of t, and t is the time constant. Follow the given steps to find out the response of the first order system. As we know, response is nothing but output. So what you have to do in this, I told you already, R of s is nothing but R of t, and C of s is nothing but C of t, and t is the time constant. So what are the steps you have to follow is, you have to take the Laplace transform of the input signal R of t. Then you have to consider the equation C of s is equal to 1 by st plus 1 into R of s, where R of s is a value which you have got already, and if needed you have to go for partial fraction. Then we have to go for applying what is C of s. So you can see over here what I have told you now. As we know that C of s by R of s is equal to 1 by st plus 1. C of s is nothing but 1 by st plus 1 into R of s. If we are considering the input as unit step, the R of s value is 1 by s. So the C of s value will become 1 by st plus 1 into 1 by s. So you have to go for applying the partial fraction. Once you apply the partial fraction, the equation will become C of s is equal to 1 by s minus t by 1 plus st. So if you take the inverse Laplace transform of the corresponding C of s, you will get C of t, which is equal to 1 minus e power minus t by t. So when t is equal to t, small t is equal to capital T, you will get C of t is equal to 1 minus e power minus capital T by again capital T, so that it will become minus 1. So equation is 1 minus e power minus 1, where the value which you will get is 0.632. T is known as the time constant and is defined as the time required for the signal to attain 63.2% of final or steady state value. Time constant indicates how fast the system reaches the final value. Smaller the time constant, faster the step response. I hope you understood the first order system. Now we'll move on to the second order system. Before moving, I just want to show you the first order system response. You can see over here the first diagram you have already seen, because unit step I have already taught you in the previous video. From that we have gone for response of unit step input of a first order system. So I told you already, here we have identified that t value is 0.632. You can see over here t value is 0.632 and it is keep on increasing depending on the t value. Hope you understood the first order. Now we will move on to the second order system. So consider the same thing what you have considered already, but the thing is, instead of first order you have to consider a second order. A system is varying. You can see that previously what you have considered is, we have taken the equation as 1 by st. You can see here 1 by st only we have taken. Now we are moving the equation into this one, omega n square divided by s into s plus 2 delta omega n. This is the system which we have considered, and it is same as that of the first order only. Only thing is the system has varied with second order. Now we have to prove that whether it is first order or second order system. So you can see, as usual, previously I have told you transfer function is identified by C of s by R of s. Equation is same, G of s divided by 1 plus G of s into H of s. Here H of s is 1. So the equation is C of s by R of s is equal to G of s divided by 1 plus G of s. So as we know, I have shown you already, G of s is nothing but the system. So the system has given the equation as omega n square divided by s into s plus 2 delta omega n. So substitute that over here so that you will get C of s by R of s is equal to omega n square divided by s square plus 2 delta omega n s plus omega n square. So here you can see, as we have discussed already, power, order, something I was telling you, remembering? So there we have seen that if you see the order as 2, or if you see the polynomial as 2, denominator polynomial as 2, then we can consider it as second order. You can see over here the power of s is 2 in the denominator term, hence the above transfer function is of second order and the system is said to be second order system. So you have to find out the characteristic equation from this. The characteristic equation is nothing but the denominator. Once you equate the denominator to 0, you can find out the characteristic equation. You can see here s square plus 2 delta omega n s plus omega n is equal, n square is equal to 0. So you have to find out the roots of the characteristic equation. You have to use the quadratic equation, it is minus b plus or minus root of b square minus 4ac divided by 2a. That equation you have substituted over here, so that you will get the answer as minus theta omega n plus omega n into root of delta square minus 1. So the two roots are imaginary when theta is equal to 0. The two roots are real and equal when zeta is equal to 1. The two roots are equal but not real when zeta is greater than 1. The two roots are complex conjugate when 0 less than zeta less than 1. So we can also, previously also we have seen, we can write this as same thing for second order also. C of s is equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square into R of s, which we have done previously. Is it was C of s into 1 by ts plus 1 into R of s. Same thing we have done over here. It has to be written here also. You can see here what you have written there. This equation, C of s is equal to 1 by st plus 1 into R of s. Similar way we have written for second order system also. So the conditions they have given over here, zeta is equal to 0. So it has to be, I told you already, here you have given this condition, zeta is equal to 0, two roots are imaginary. You can see here, roots are purely imaginary and the system will call it as undamped. I am giving you new information over here, which we have to remember always. We have 4 kinds actually: undamped, critically damped, overdamped, as well as underdamped. These 4 we have to study now in future. So just remember all those things. When zeta is equal to 0, roots are purely imaginary and the system is undamped. When zeta is equal to 1, it will be roots are real and equal and system is said to be critically damped. When zeta is greater than 1, it is a real and unequal and the system is said to be overdamped system. When zeta is 0 less than zeta less than 1, in that condition we will call the roots are complex conjugate and the system is underdamped. And now we can see another term over here. In this equation we have seen that zeta 0 means it is plus or minus j omega n, zeta 1 means minus omega n, zeta greater than 1 is minus zeta omega n, plus or minus omega n root of zeta square minus 1. And when 0 less than zeta less than 1, the equation is minus zeta omega n plus or minus j omega d. And omega d is a new term which you are studying over here, which you will call it as damped frequency, and the unit of this damped frequency is radians per second, and the value which you will calculate is omega d is equal to omega n into root of 1 minus zeta square. So you have seen all these equations over there. So in this, so you can see over here notations, it is same only, it is not different, it is same only, but the way that they are written is different only, but both the things are same only. So you can see ZFS is the output signal, RFS input, omega n is natural frequency, and I was telling about omega d. Omega d is nothing but frequency of oscillation, damped frequency of oscillation, and zeta is nothing but damping ratio. Previously, we used to see where everywhere we have seen zeta, we are telling that zeta is nothing but damping ratio. What is damping ratio? I have written over here. Damping ratio is defined as the ratio of actual damping to the critical damping. So it is, so the response C of t of second order system depends on the value of damping ratio. Depending on the value of zeta, the system can be classified into 4 cases. First one is underdamped, zeta 0. Second one is first one is undamped, zeta 0. Second one is underdamped, 0 less than, zeta less than 1. Third one is critically damped when zeta is equal to 1. And fourth one is overdamped where zeta is greater than 1. So this is about second order. I have given an overview of second order systems. Now after this we will go for seeing each and every topic. I told you already 4 topics are there: underdamped, undamped, overdamped as well as critically damped. So next topic which we are going to see is undamped and underdamped. Thank you.